Why is it?
Huh? You don't need it. I don't care. I just want to know what V is in terms of delta Y. So this was the ring. This is the thin hoop.
Where's your
1/2 V squared plus 1/2 V squared is V squared. That's fractions. Yes.
Why is this?
Omega squared. And so I'm substituting in V over R for omega. So V over R squared. So you square the V and you square the R.
Is that?
Omega is V over R.
Oh, okay, that.
Got it?
Yep.
Yeah. So, are we there?
We don't know what she.
Are we there? Right? This is thin hoop. This is thin hoop. My spheres, you guys should have ended up with 10/7 delta Y. Am I right? My spheres should have ended up with 10/7 G delta Y. So, why does the sphere dust the hoop? This is sphere. That's thin hoop.
Its velocity is just bigger.
Isn't it? Right? Isn't root 10 over 7 bigger than 1? See what I'm saying? Root 10 over 7 is bigger. So, of course, this velocity, this is the translational velocity of the sphere at the bottom of the incline. Will all spheres always have this velocity at the bottom of the incline?
Yes.
Always. It has to. It does. Which just blows my mind. But it does. So, the sphere will always be root 10 over 7 faster than the thin hoop. Always. Yeah.
So is that? Oh wait, never mind. Yeah.
Now, I'm not asking you to, there's no reason for you to memorize this. That's a ridiculous thing. Are you guys learning just how much there is to have in your heads? So this is not one thing that you need to shove into your head. The only reason why I even have this stuff memorized at the moment is because I've done this 5 times today. And so now these numbers happen to be in my head. It's not something that you could come up to me in a month from now and tell me, so this is the sage. What exactly is the velocity of a thin hoop at the bottom of an incline? I don't know. And so the cylinder is root 4/3. Is that right? Cylinder? Is that what you guys got for cylinder? You should have. Root 4/3. So, will the cylinder beat the thin hoop? Yes. The cylinder definitely beats the thin hoop. And won't the cylinder always be close? He's close to the sphere, but he's not exactly at the sphere. Right? So now if you compare this to I, the mistake that you guys make, the total mistake that you make was you were thinking about, well, if I have a bigger I, then that means I'm going to be going faster, right? You guys made that misconception. Is that true? No. So what is I? What does I mean? What does I have anything to do with? Well, backtrack a little bit. If something has a big mass, does it want to move? No, right? A big mass doesn't want to move. But once I get it moving, is it hard to stop? Yeah. That's inertia. That's plain old inertia, right? Mass is talking about plain old inertia, how hard it is to move something. So I is rotational inertia, how hard it is to get it to roll or rotate. So the bigger the I means the thing is really hard to rotate. Does that make sense? The smaller the I makes it easier to rotate. So the smaller the eye, the easier it is to roll, right? So therefore, that will change how it translates. Yeah.
So it might be kind of a stupid question, but are we ever like do they ever calculate the eye of like things that have flat surfaces, like things that roll on their like pointed edges? You know what I mean? Like if you like pushed a cube down a hill, or do they just do like flat surfaces?
Yes, I'm sure you could figure out the moment of inertia of something that is a funky shape. Yes. Yes. So, but it would be a big eye. Anything can have an eye, can have a moment of inertia. The human body has a moment of inertia, right? And the moment of inertia is always considered about a certain point, right? So we'll talk a little bit more about that in just a second. So, imagine you have a ring, right? I always feel bad for the ring because it always loses. Poor ring. Always lose. So the moment of inertia of the ring is, what is it? mr squared? mr squared? Okay. That's my hoop. That's my thin hoop. But I can start altering its moment of inertia by changing it. So I could increase its mass, right? I could change its radius, or I could do things like this. What did I just do to my ring? Did I increase its mass or decrease it?
You decrease.
If I put spokes in there, did I just increase it or decrease it?
Increase.
I definitely increased that moment of inertia, right? And the more spokes I put in, what's going to happen? The more it increases. Doesn't it make sense? So let's put, well, hold on. I want to change the spokes that I put in here because I accidentally drew that so that it was hard. I'm going to put 3 spokes. I just increased its moment of inertia by how much? Well, how many spokes did I just put in there? 3. So my new moment is going to be I hoop plus 3 spokes. So now look at look at your chart, and what do the spokes look like?
Long uniform rod.
So they're long uniform rods. I buy that. Is it a long uniform rod about its center point, or is it a long uniform rod around its end point? Around its end point, yeah. So it's 3 eye rods about their end points. Okay. So is that going to be difficult to look at a shape and figure out how to do compound eyes? Yeah. You just add stuff together. Make sense? Right? And by adding more and more shapes to it, what happens to the total eye? It increases. And the higher that eye goes, the less likely it is to get going. But once it's going, what happens? It's hard to stop. It's really, really hard to stop. We use something like this. They're called flywheels. It's really, really cool. It's called regenerative energy. So they put them in fancy cars. You've got a flywheel in there. So as you brake, the energy from the braking spins up a flywheel. And so you turn your translational kinetic energy, right? You're moving translationally in a straight. You store that energy in a rotating flywheel. So you're sitting there at the stoplight. Where's your kinetic energy? In the flywheel. And then once you let off the brake, what do? You use that rotational kinetic energy gets used again to get your car to do what? Start going again. It's really cool. It's really, really, really cool. All right. So let's say we have a merry-go-round. It's got a radius of 3 meters. And we're on our merry-go-round. We're standing here at the edge of our merry-go-round. We've got a mass of 60 kilograms. And we're having a good old time. It's rotating 4.2 radians per second. Woohoo! Having a good old time. I know. I think there are a few playgrounds out there that still have merry-go-rounds. So you're rotating, woohoo! Is that fast? Pretty fast. Having a good old time. Having you on the merry-go-round. Does that increase or decrease the total rotational inertia? It increases it, without a doubt, right? So, in order to know the total rotational inertia, wouldn't we have to know what the inertia of the merry-go-round is, MGR, merry-go-round, plus add your rotational inertia. All right, so your rotational inertia. Now you yourself are not spinning, right? You are rotating about a point, aren't you? What is it about you that is rotating about the point? Your center of mass, right? Isn't your center of mass rotating about that point? So how do we calculate a moment of inertia for a center of mass going around a point? Isn't it just mr squared? Right? That's just mr squared. Your center of mass is rotating about a point. So this, for lack of a better title for it, it's just the moment of inertia of a point, right? Which you don't have on your sheet. It's not on your sheet, but are you supposed to know what it is? Yes. Yeah. So let's say the moment of inertia of the merry-go-round is 1,400 kilogram meter per second. I'm sorry, meter squared. I said meter per second. Kilogram meter squared. So I want to know the total rotational inertia. You would do the 1,400 kilogram meter squared plus your mass, 60 kilograms, times that 3 meters squared. So that total rotational inertia is... What a great year. I don't know, I wasn't alive.
Not so good.
Could have been a good year for somebody. You're awfully American-centric, aren't you? Come on. Could have been a great year for somebody. Right? Don't tell me it was a bad year for everyone. If you had a friend riding on here with you, does that increase or decrease the moment of inertia? Increases it even more. If you had another friend on there, right? The more people you have on there, the bigger the moment of inertia. Makes sense? Right? So if you had you and all your friends on there, then would it be easier or hard for the one person who's off the merry-go-round to get it going? Hard. It's hard for the one person off there to get it going. But once you've got it going, then what happens? Right? It sucks to be the one person who's pushing, but once you're on it and you're going, won't you stay spinning longer? Does that make sense? Right? That's kind of cool. Oh, if only we could go and play on playgrounds now that we understand physics. So, for some reason, you're the poor lonely kid, and so you're on the playground, and you've got your merry-go-round, you got it going, and you hopped on. Woo, you're on it yourself. Don't tell me that you didn't ever get on a merry-go-round all by yourself. You did. Yes, you did. Some of you are like, so you're on your merry-go-round all by yourself. You decide to walk to the center of the merry-go-round. Right? So it's spinning, and you're walking to the center of the merry-go-round. Are you increasing or decreasing the moment of inertia?
Decreasing.
You're decreasing the moment of inertia. So by decreasing the moment of inertia, what happens to the merry-go-round? Oh, it wants to spin faster, doesn't it?
No.
Doesn't it? If I decrease the moment of inertia, doesn't it make it easier to spin?
It's like you put your arms in.
So, just naturally, because you are awesome, you automatically recognize the conservation of angular momentum. Coal. You're not riding a cup, you're riding a coal. Coal is cool. It's an umlaut. my German-speaking friends. Coal is cool. Yes, there are some German-speaking friends in here.
Oh yeah, raw.
Yeah. Cool. Get it? Cool. It's cool. It's an O with an umlaut.
Okay.
That's what those two dots are called.
I know.
Conservation of, what's the L stand for? Angular momentum. Yes, angular momentum. So, L is angular momentum. What's linear momentum? P. All these letters. I don't know why they do it. I apologize on behalf of, for regular old linear momentum. MV. So playing the game that we are getting used to, right? Linear momentum is P, angular momentum is L. Instead of M's, we write I's. Instead of V's, we write. It's not a W. It's an omega.
What does W stand for?
Huh?
What does W stand for?
Work?
Omega.
Oh.
Yes.
Previous two formulas on the angular side, does the theta stand for delta theta?
Sure.
So it's like the angle version.
Sure. Yes. Don't you have to move through some theta? So therefore you change the theta? Yeah. Right? You are, by virtue of the fact that you're moving angularly, that theta is the what? Yeah.
So for every revolution you allow this to pass.
Yes. Yes. And that's where we started over here. Right? Yes. Exactly. Alrighty, so when you were standing here, was there angular momentum?
Yes.
Sure, there was angular momentum. You had some initial moment of inertia, I, some initial rotational inertia, and you were angularly moving, I omega. That's what you began with. You walked to the center of the merry-go-round. So after you walked to the center of the merry-go-round, didn't you change I? So you have to have changed omega, right? If you decrease the I, what did you have to do to the omega? Increase it. You have to. It's a law. Law of conservation of angular momentum. So we can go ahead and we can plug in. What was our original I when we were standing there on the edge? 1940? 1940 kilogram meter squared times what was our original omega? 4.2? 4.2 radians per second is equal to, once we are at the center, what's the I?
1400.
Just 1400. And so we can calculate omega. I like angular momentum. Angular momentum is pretty easy.
5.82
I don't know.
radians per second.
.82 radians per second. And you're absolutely right. Some of you have figured it out, and you're like, oh, so that's why ice skaters do what? They pull their hands in. It's angular momentum. As they're out here, don't they have the mass of their hands? The mass of their hands are some r away from their body. And that's assuming that their arms don't have any mass, which, bad assumption. But, right? The mass of their hands are out here. And so you've got mr squared out here and you've got mr squared out here, and so you are rotating and the I is big. As you bring these in, what happens? Right? You decrease that I, and so you've got to spin faster. An ice skater, I'm not. I always kind of wanted to be because they got to wear fancy outfits. Fancy outfits, right? So if I were an ice skater, then I think that I would have my costume designer make sure that I had really heavy bracelets. Wouldn't that be smart? It would make my ice skating look better. Because if I've got really heavy bracelets, then what's going to happen to how big of a difference there is between the velocity?
Increase
Yeah, it would increase the difference, and so it would look really cool. I could spin really, really fast because I've got these big heavy bracelets on. Cool. Yeah.
So once you reach the center, isn't the radius technically 0?
For you,
So wouldn't
not for the
so
right.
it's
The
still-
merry-go-round still has its inertia. Yeah, you are no longer adding to the rotational inertia of the system. Yeah.
So does having a smaller eye make you go faster?
It makes it easier to rotate. It makes it easier to rotate.
So the smallest, so the thing who has, or the sphere has the smallest eye. 'Cause it's
So-
rotated, went faster, right?
No, we were figuring out linear velocities. Right? Yeah. Yeah,
So
it's
that depends on the
confusing.
radius too.
Wait.
Uh-huh. Because I'm not finished teaching. Good so far? Alright. Girls, to split up the work. Girls, I want you guys to figure out the original kinetic energy. The original kinetic energy when you were still standing out on the end. Guys, I want you to figure out the new kinetic energy when you're at the center. So girls when you're on the outside, guys when you're at the center. The kinetic energy. So what kind of kinetic energy do we have? Do we have translational kinetic energy or rotational? Rotational. Yeah, we definitely have rotational. Be careful with your I's and your omegas. Use the correct I's and omegas. Girls,
17,100.
say it again.
17,111.
Yes? Jules? Right? That was initial? Girls, yes, nodding. Guys?
23,711.
Does that make anybody want to furrow their brow and go, huh? We started with 17,111 joules of rotational kinetic energy. We end with considerably more. That should make us all go, what? That seems weird, doesn't it? You don't usually end up with more energy than what you started. Are you allowed to end up with more energy than you started? No, because there's a little law called the conservation of energy. So, how did that happen? We didn't do anything wrong. In order for me to walk to the center, was that an easy thing to do or was that a hard thing to do?
Hard.
That's a very, very hard thing to do. If you've ever tried it, it's really hard to do. So to walk to the center around takes work, doesn't it? Didn't I have to eat my Wheaties to do it? Oh, so since I did work to the merry-go-round, did I change its kinetic energy? Did I do? How much net work was done? How do I figure that out? I subtract. Oh, wait, isn't that Ewok? Oh, that's Ewok. And so I think you had a problem last night, which you may not have recognized. You needed to know how much net work it was. But it was easier than this because why? One of them was, yeah. So the network was the kinetic energy. It's kind of cool. Get it? It's kind of cool. I know. All right. Back to my merry-go-round. Here's my merry-go-round. It's 3 meters. What's the radius? And my merry-go-round has come to a stop. So it has quit rotating. So now I'm just standing there lonely on my merry-go-round, all alone. Wasn't I alone to begin with? Think about it. If you get it spinning, can't you just like run back and forth on it? And as you go towards the center, what happens? goes faster, and then you run back out. What happens?
Slows down.
Slows down. You go towards the center. It
Speeds up.
just run back and forth. Can you do the same thing in a spinning chair? Can you do the same thing in a spinning chair?
Yeah,
Can't you
right.
get a spinning chair spinning, and then what do? Put your hands out, put your hands in, put your hands out, put your hands in. Don't tell me you haven't played in a spinning chair before. You kind of want to play in a spinning chair.